Right. Okay. So we discussed about the magnet rules. So basically, it is just like poles. So for example, let's say North Pole and the North Pole, they repel, and we do have the South Pole. South Pole, they again repel, right? So like poles repel, and unlike poles, for example, let's say we do have the South Pole and the North Pole, or probably North Pole and then South Pole. They always attract. So these two facts together, like poles repel, unlike poles attract, right? This statement is called magnet rule. Okay, so now in case they will ask, as I mentioned earlier, in case they will ask about this in your paper, so what is meant by the magnet rule, or just state magnet rule? So you have to write the like poles repel, comma, unlike poles attract. So that's the magnet rule. Okay. So with that one, we can just look into the next important the topic. So now we so far we discussed about the magnets, and then like the magnetic materials and all these stuff, right? And now we are going to pay a bit of attention how to make a magnet. Now, for example, by using a magnetic material like iron or the steel, one of the frequently used materials to make magnets. So something like that. So just by using one of these magnetic materials, how we can make a magnet. Now, actually, there are two basic methods, right? Single touch method and double touch or divided touch method. Basically, we can say we do have something called single touch method, right? I'll write this somewhere here. So number one is called the single touch method, and number two is called the divided touch. Or sometimes we say double touch. Right. Don't worry, we are going to discuss about these things and how this thing can be done. Now, actually, out of these two methods, right, the first method, single touch method is the one you are intended to go through at this age, right? So you can get to know about this divided touch method little later, right? While you are doing your advanced level, right? So for the time being, just we are going to stick to this particular method, single touch. Now, the slide says we can use a permanent magnet to magnetize a piece of iron or steel. Now, one of the very important facts you have to remember, you have to bear in your mind, is that in order for you to make a magnet, you have to have a piece of magnetic material. Now, we talked about a lot. We talked with details, we talked about magnetic materials, right? So the materials or substances which are getting attracted to magnets are called magnetic materials. Now, for example, we said we just named a few, just the iron and then steel. We said about we talked about the cobalt, nickel, and then the neodymium, right? One of the very, very frequent examples. And alnico, chiconal, alchemax, all these are very, very important alloys, industrial level alloys. Okay. Now, if you take, for example, something which can be found very easily is going to be either iron or steel. Now, steel is highly recommended in this case. There's a reason why. We're going to talk about that thing towards the end of this presentation, right? Wait for that, right? I'm going to keep you a little bit ahead than your colleagues. By giving that knowledge as well. In case we can find out a piece of, like, let's say piece of iron, or as the a piece of steel, I mean, it's perfect, right? Okay, so now as we shown in this diagram, so the steel bar, now for example, let's say the steel bar, right? So this word is very important, the steel bar, or just probably you can say the iron, the rod, or piece of iron. So either one will work, but steel bar has a, like, you know, difference, or just, I mean, the steel bar will work, I mean, too much better than the iron rod. Why? The reasons we are going to discuss the in a while, I mean, towards the end of this presentation, as I mentioned earlier. Okay, now we can use a permanent magnet to magnetize a piece of iron or steel. Now, for example, let's say we have already selected a steel bar, I mean, a piece of steel, right? So how we can do this? Now, stepwise, I mean, those steps have been mentioned. Lay a piece of iron or steel on the table. Number one is once you get that steel bar, just, I mean, place that thing on top of the table, right? Or just, I mean, the bench, right? Or the just your, I mean, probably on the floor, doesn't matter, right? So a place which can be reached comfortably. Okay, then number two, so obviously step number one is going to be that. Then step number two, using one pole of the magnet, I mean, permanent magnet you're holding in your hand, because we said at the beginning we need a permanent magnet for this process. So now when you have that permanent magnet, you know there are two poles. One side is going to be the North Pole, and on the other side we do have the South Pole, right? So you can use either South Pole or the North Pole in this case. It doesn't matter. I mean, whatever the pole you're going to select, you don't have to worry about that thing. Definitely that the steel bar is going to be a magnet. Actually, strictly speaking, a permanent magnet, right? Depending on how many times you're going to, I mean, do this process effectively. Okay. Now, using one pole of the magnet, stroke the iron or steel piece gently from one end to the other. Very important thing. So, not all the way here and there. You have to follow a particular method, right? Mentioned here. So now, from one end to the other end. Now, as shown by this particular diagram, right? So let's say, I mean, as shown by this diagram. So they have shown this particular way, the cycling pattern of this the bar magnet, right? I mean, the way that bar magnet should be carried on top of this steel bar. So now in this case, from here to there, right? You have to keep in your mind, if you take this North Pole, which is in touch with the steel bar, here and there, the way you want, right? It is not going to work. Probably it might work, but it is very, very inefficient. So therefore, remember always, when you're going to write your answer in your paper, from one end to the other end is something really important. Or just you can say that thing in other words, right? Like this. Only along one direction. Starting from one end towards the other end. So these alternative, I mean, the statements can be used to give the same meaning, right? Okay, so from one end to the other. And then third one is going to be just repeat this process, right? Repeat several times using the same pole, stroking in the same direction. So that is going to be probably the, I mean, most important step. Using the same pole is very, very important, right? Same pole. Just, I mean, let's say 2-3 times you're going to use the North Pole to stroke the steel bar or the iron bar, and then after that you can't remember what pole was used, right? So accidentally you're going to use the South Pole in the remaining strokes, so it is not going to work that effectively. So you have to stick to one particular pole. It doesn't matter whether it is going to be a South Pole or a North Pole, right? So just stick to that particular pole you have already selected at the outset. Now, for example, let's say you have selected this North Pole as shown by this particular figure. Just stick to the North Pole, I mean, till the end of this, I mean, procedure, right? So until that steel bar is being stroked. So just, I mean, like, until the process is over, right? Okay. So stroking in the same direction is going to be the second point I want you to remember. completely, right? So actually this process is called the single touch method, right? So it's called the single touch method. Now, why it is called single touch? Because we are using only one bar magnet throughout the entire process of making this magnet, right? Okay, so then that's called the single touch method. And number two, just you're going to use only one particular pole. And number three, to be remembered, right? So always it should be along one particular direction. From one particular end towards the other end. So you have to stick to that particular procedure in order to make this steel bar or the iron piece or the iron bar or the iron rod, right? Or we can say iron stud magnet, right? Okay. So if I summarize, if I just consolidate these steps. Number one, you need a piece of let's say the steel, right? Or probably you can use iron in case you won't be able to find out steel. Steel is highly recommended for reasons I'm going to explain later in this presentation. Number two, you have to use the magnet. Let's say you have to have a permanent magnet already with you, right? Permanent magnet. The permanent magnet. And then not only that, right? You have to have a permanent magnet. Let's say okay, so let's increase one more step and stick to one particular pole. Stick to one pole. It can be either north or south, as I explained earlier, right? But you have to make sure you're going to stick to always that particular pole you selected at the beginning, right? Okay. And number four, the last but not the least, right? So it should be taken, stroking that piece of iron or the piece of steel should be done along the same direction, along one particular direction, right? So it should be along the same direction. Stroking should take place, right? Stroking should take place along the same direction, along the same direction. Okay, so these are the steps. You have to remember. Yes, you need a steel bar or piece of iron, and then you need another permanent magnet. Then you have to stick to one of these poles out of two, right? Throughout the entire procedure, and you have to take this particular pole of the permanent magnet while stroking the steel bar, right, along one particular direction. Towards the end of the process, definitely the piece of iron let's say the steel will have become a permanent magnet. Okay, congratulations with that. And then we are ready to get into the next topic. Okay, so let's see what is that. Now we talked about all magnetic materials, and then just a while ago how to make a magnet just by using iron bar or probably steel bar, right? And by using a special method called a single touch method. Now we are about to discuss something called magnetic field patterns, right? Now there are a few questions. Now when it comes to magnetic field patterns, there are a few questions. What are meant by magnetic fields? Now we heard about paddy fields. I'm pretty sure you have heard about paddy fields, right? So now what is really meant by a magnetic field? And then why we take this particular word pattern. Now, the pattern is something which is getting repeatedly, right? Or probably something which is iterating, recurring, right? Something which is getting repeated. So we'll make a pattern, right? So something like that. So if you draw a straight line in a particular direction, right? So if you keep repeating, drawing the same line segment along the same direction, right? So definitely you're gonna create a pattern. Somebody who's going to look into that diagram will identify there is a pattern here. Even the numbers, right? But sometimes on your t-shirt, which you're wearing right now, you can look into that. Sometimes you can find so many patterns. When it comes to a pattern, actually the characteristic of the pattern, right, is that something is getting repeated, or we can say something is getting iterated, or something is occurring, recursively, right? Okay. So now magnetic field patterns. Now you can see here we have something, really familiar to us, right? So we do have this, what's called this North Pole, something we discussed, and we do have the South Pole, right? And we have a few, lines. Sometimes some lines are the curved line segments with arrowheads here, right? And we can find a few lines are straight lines, again with arrowheads. And these arrowheads are not along the same direction, right? These arrowheads are having different directions. Now we have to find out why the lines are there, why some lines are straight, why some lines are curved, and why we do have arrowheads along different directions. Okay, right. We are ready to get the step to answer all these questions. Okay, right. So let's look into that. Now, magnetic field is something let's say actually some area, some region within which that magnet is going to spread its power. Now when I say magnet is going to spread its power, what do you mean by this? Its power, right? Its ability to attract a magnetic material. So now if you take a magnet, that magnet is going to have a certain area in its surroundings. If you place a magnetic material inside that area or the region, that magnet will be able to attract that magnetic material, right? So if you place that magnetic material beyond that region, so magnet won't be able to detect that magnetic material, which means magnet won't be able to feel the presence of that magnetic material. So therefore, magnet won't be able to attract that the magnetic material. For example, let's say now if you take like the magnetic material, let's say for example the piece of iron, right, or at your home, and you have so many permanent magnets in your school laboratory, do you feel, or just when you take these the magnetic materials, or when you take that piece of iron into your hand, you feel an attraction to those magnets which are staying inside the school laboratory? What do you say? Surprisingly, no. You won't feel no attraction at all. It is impossible. The main reason now should be obvious to you, because that magnetic material, piece of iron you are holding in your hand, being at home, is completely outside, that particular region of the permanent magnets, right, within which they spread their power. So that region is called the magnetic field. So now what we can say, just by using these scientific words, we could have answered very easily and let's say accurately and shortly. We could have answered like this. Now when you have piece of iron at your home, and when you have the permanent magnet in your school laboratory, right, so that piece of iron is far enough, or just the far away from the magnet which is in the school laboratory, in such a way that that piece of iron is outside the magnetic field of the permanent magnet which is inside the school laboratory. So therefore, that even though iron is a very strong, very good the magnetic material, it is outside the magnetic field, the area within which magnet spreads its power, so that simply magnet won't be able to feel that the piece of iron. So it won't be able to detect that piece of iron. So it won't be able to attract that piece of iron, that area, right? So now what do you mean by basically what do you mean by the magnetic field? it is the region within which magnet spreads its power, its magnetic power, right? Okay. So now when it comes to the slide, it says the area around a magnet where it can attract a piece of magnetic material is called the magnetic field. Obviously, yes, right? So it's the region, the within which a magnet is capable of attracting a magnetic material. So in case the magnetic material is placed outside the area, outside that region, magnet won't be able to attract that magnetic material, even though it is magnetic, won't be able to attract, right? And so inside the magnetic field, so that piece of material will be, magnetic material will be attracted by the magnet. If the magnetic material is outside the magnetic field, so magnet won't be able to attract that piece of magnetic material. Simply, it is going to work that way. Okay, so let me, illustrate that fact, in a way that you can understand, right? Really clearly. So if I'm going to take let's say, for example, if I take bar magnet somewhere here, say, okay, fine, we can take this one. So now, let's say this is the region. Okay, we have a bar magnet here, right? So red end, fine. So it's going to be the North Pole, and we do have the end of the that blue region is going to be the South Pole. That's how we should. We color even in practice, we use that red color to represent the north side, and usually we use that blue color to represent the South Pole. The region of the South Pole. Right now, I have drawn a rectangle. You can see, right, to represent the magnetic field. Now, again, what do you mean by, just recall the meaning of magnetic field? So it is the region, right? It is the region. So we can say the region or the area around the magnet, right? So a piece of magnetic material can be attracted by the magnet. Simply, that's the idea, right? So, in case they will ask in your paper, what is meant by a magnetic field? So, you don't have to panic. Number one is that you have to be kind of like, so you have to be so relaxed, and then just you can write the answer. You can recall the key points. There should be a magnet, and there should be a magnetic material, and there is a region, in the surroundings of the magnet. Now, this region, okay, so in which, or just we can say within which, that magnetic material will be attracted by the magnet is called the magnetic field. In case that the piece of material, or let's say that piece of iron or piece of steel, right, is outside the magnetic field, that magnet won't be able to attract the piece of iron. Basically, that's the idea, right? Okay. So now, just I'm going to have a different color, and let's say I'll select let's say place like this. Okay. So probably it is not that visible, so let me use that color. That's not that visible, it seems, right? So we can use a different color. Let's say I'm going to use red color, right? Okay. So let's say maroon color, or probably what is the green color. Now, if I go for likely say area like that, or some area like this, or a place like that, or a place like this, what is it? Now, all these spots, right? Let me just write spot number 1, spot number 2, spot number 3, and spot number 4. All these spots are within the magnetic field of the bar magnet. So therefore, in case you will place, let's say a piece of iron here, piece of iron there, piece of iron here, piece of iron somewhere there, here, right? So all these iron pieces will be attracted towards the magnet. Without having any doubt, right? so will be completely attracted towards the magnet. So let me show that thing by using a different color. So this piece will be attracted towards the magnet. This piece will be attracted, and this one will be attracted. This one will be attracted towards the, most probably towards the poles of the bar magnet. So what do we understand by that? The attraction. So spot number 1, spot number 2, spot number 3 and number 4, all these are within the magnetic field of the magnet. Right. So now, for example, if I'm going to select another area, probably the lying outside, somewhere there here, let's say, and another one somewhere there here, another one somewhere there here, another one probably somewhere there here, right? What do you think? Probably now you can guess, right? So let's say I'm going to say this is a simple A, that is going to be simple B, that is going to be simple C, this is going to be simple D. Now, what do you think about A, B, C, D areas or spots or places, locations? What is it? All these A, B, C, D locations are lying outside the boundaries of the magnetic field. Now, the boundary of the magnetic field is this, brown color rectangle, inside which we do have the magnetic field, outside which we do not have the magnetic field. So simple A, simple B, simple C and simple D spots are lying outside the magnetic field. So therefore, in case you will place, let's say, a piece of iron somewhere there here, right, it won't be attracted by the magnet. Or at the place of B, won't be able to attract. And the place of C, will not be attracted. D, bar magnet is completely unaware about the presence of the magnetic materials at places A, B, C, D. So therefore, magnet won't be able to attract those materials. I think you got the, complete idea what is meant by the magnetic field, right? Okay, so basically it is going to be the area or the region around a magnet where or within which it can attract a piece of magnetic material, right? Okay, so that entire definition is given here. So just you can keep the thing in mind, right? So that's the area around a magnet, right, where it can attract a magnetic material. That is called the magnetic field. Now, from your lower grades, we have handled so many magnets, right? So many magnets, in different the experiments, probably just while playing. But have you ever seen these magnetic, this magnetic power? Or just some lines are going away from the poles of the magnets or coming towards the poles of the magnet or something like that, a pattern like that. Unless otherwise you used a special method like iron fillings or probably dry grass seeds, right? Something like that. So without using any special materials, have you ever seen some kind of pattern which surrounds a given bar magnet? What is it? No. So which means even though magnetic fields are there in the surroundings, in the vicinity, in close proximity of a given magnet, right? Those things are really invisible. So another important fact you should remember is that magnetic fields are invisible. They are invisible. We can't see them. Actually, they are, out of our vision, right? We can't see them. But actually, we can use some methods, right, to, figure out, to get to know how the magnetic field shape is going to be. The shape of the magnetic field is going to be how? Whether it's going to be something like rectangle or something like a triangle, something like a circle, or it has a different shape, right? So we can investigate the shape of the magnetic field by using different methods. Now we are about to talk about that thing. Okay, so now one of the very the frequently used method is to use a compass. Now compass itself is a tiny magnet. So therefore, usually, now we have discussed about that property of a magnet. Now, when we talked about that thing in all these early the steps, right? So when a magnet is freely suspended, it is always going to align the south direction, right? So of the magnetic field of the Earth. And we discussed about the North Pole, how to identify the North Pole of the magnet. That is the one which is always directed or heading towards the magnetic North Pole of the magnetic field of the Earth. And the one which is heading towards the south magnetic pole of the Earth, is the south pole of the bar magnet. Now, having these ideas in your mind, just we can use either that method or is just these compasses. So usually we say plotting compasses. Why we say plotting? Because we can just get to know about the shape of the magnetic field by using these compasses. Okay, fine. It says there are two ways. Something really important. There are two ways to illustrate the shape of the field around a magnet. Number one, using iron fillings. Now, something we have done, in our lower grades, right? Something which was really fun. We sprinkled the tiny pieces of the iron or probably steel, right, which can be found readily by using one of these, the shops in which people work with iron. I told you about this thing the last time also. Now sometimes there are shops. They use machines to drill and to make holes, to the shape, to pile, right? So while these processes are going on, so tiny pieces of iron, which are called iron fillings, are getting removed. Actually, chips of iron are getting removed. So usually people collect them so that they can sell those things for different purposes. So in school laboratory also we can find the iron fillings. So in case you are going to sprinkle the small amount of iron fillings, right? In the surroundings of a bar magnet, or probably horseshoe magnet, or ring magnet, or flat magnet, right? So these iron fillings are going to, get aligned in a certain manner. They are not going to stay the way you sprinkle them, in the surroundings of the magnet. Instead, they keep moving here and there. Slowly they keep moving here and there, and they are getting just into a certain pattern, right? And let's say you did that and you removed the iron fillings, and again you are going to sprinkle iron fillings in the surroundings of the same bar magnet. What do you think? So iron fillings are going to get a different pattern, or iron fillings are iron fillings are resembled into the same pattern it formed the last time. What do you say? It should resemble the same pattern. Why? Because it is the same bar magnet. So therefore, the magnetic field of the bar magnet is not going to change. It should have the same pattern in case, right? So magnetic fillings, magnetic field is, magnetic field. The shape of the magnetic field will be reflected by the patterns, or just by the sprinkled the iron fillings. So showing the same the magnetic field pattern, right? So therefore, just we can get to know about this the shape of the magnetic field. Just we can visualize about this magnetic field. The shape of the magnetic field just by sprinkling the iron fillings, or just spreading the iron fillings in the surroundings of the magnet. So method number one is going to be that, right? So the most simplest method. And number two is a little scientific as well as a little professional, we can say that way, right? So plotting compasses show the direction of the field. Now, for example, if you take the few compasses and if you locate them in the surroundings of a magnet, for example, as shown by this figure, in the surroundings of a bar magnet. So these needles of the compasses are going to align in certain directions. Now, for example, let me show you by using the few arrowheads, right? So now, let's say this plotting compass right here. So it is showing that particular direction, right? And if you take this plotting compass, it shows that particular direction. Okay, so if you take this plotting compass, it shows that particular direction. If you take this plotting compass, it shows that particular direction. If you take one of these, another one, let's say for example this one, it shows that particular direction. So these plotting compasses are showing the direction of the magnetic field at that particular point, right, at which compass is placed. Okay, that's the most important thing. Now that compass is showing that particular direction. This compass is showing the direction of the magnetic field at that point, and this compass is showing the direction of the magnetic field at that particular point, and so forth. Like so, we can get to know about the direction of the magnetic field, right? I mean, along which direction this magnetic field is, right? So we can get to know about that thing by using these plotting compasses. So if we are going to just consolidate what we discussed, what we absorbed, what we got to know by this explanation is basically what is meant by a magnetic field. It is the region or the area around a magnet where a magnetic material can be attracted by the magnet. Basically that's the idea. And then how we can get to know about the invisible magnetic field, right? So magnetic fields are invisible, we can't see them actually, so they are out of our sight. So but we know there is a magnetic field, so how we can at least how we can get to know about the shape of these magnetic fields. What do you say? Just by using one of these methods out of two, right? The first one is going to be the most easiest one. Just by using a few iron fillings sprinkled in the surroundings of a bar magnet, or just we can use the plotting compasses. Okay, so have to remember one important thing as I illustrated by using arrowheads here, right? The green color arrowheads. So needle of the compass is always showing the direction of the magnetic field at that particular point. That is something really important. Okay, so we got the ample information, right? Ample understanding, really good understanding about the magnetic field and how we can get to know about the shapes of the magnetic fields. So with that one, we are ready to get into the fact, one of the very important topics, magnetic field lines. Now what I meant by magnetic field lines. Now magnetic field lines are basically the shape, right, or the direction of the magnetic field. So always we are using magnetic field lines to illustrate, or we can say just to visualize, to show the magnetic field of a magnet. Right, so we are about to investigate some of these properties of magnetic field lines. Probably you have seen magnetic field patterns in books, right? Probably in the internet, right? Many places like this, they have drawn the few lines in the surroundings of the magnet and then associated with the arrowheads, right? So these things are very, 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 very common. But let's see how actually they are going to work in your context. Okay. Now, next one. Magnetic field lines are used to represent a magnetic field. Now, in case in the paper they will ask, what is the primary purpose, right, or the main purpose of a magnetic field line, or what is being served by magnetic field lines? So that's a direct answer, right? So what's the answer? Magnetic field lines are used, or they represent the magnetic field, right? So we are drawing lines to represent the magnetic field. So basically that's the idea. And then properties wise, we do have few important properties. They are imaginary lines, and otherwise we draw to represent the magnetic field, right? So magnetic field lines are imaginary. Actually, we don't have some lines like that in the surroundings of a bar magnet. We have never seen, and they are not there. And so otherwise we draw them come on, the to illustrate. Okay. Number 2, they start from North Pole and end up to South Pole, or just something like they go till they are going to meet South Pole. Now, if you take one of these figures, let's say, for example, if I'm going to pay attention to this one, right? This particular bar magnet, right? So now you can see the field lines are starting from the North Pole and they go and touch the South Pole. So it's always from the North Pole towards the South Pole, something really, really important. The direction is going to be always from the North Pole towards the South Pole. Let me use something different. It should be always along that direction. Something really, really important, right? Okay, just you have to remember that thing. Why? Because probably in your paper they can give you a bar magnet, something, just a bar magnet with the poles north and south, right, on either end, and just the bar magnet, and they want you to create, or they want you to draw the expected magnetic field pattern, or probably they want you to draw about 4 or 5 field lines to represent the magnetic field of the given bar magnet. You should be able to accomplish the task, right? Okay, so let's do that thing, as an exercise, right? So for example, let's say we will, okay, I will take a different color to represent the bar magnet, right? Let me take this one, and I'm going to say, okay, fine, let that one to be the bar magnet, and okay, let's say here we do have the North Pole, let's say here we have the South Pole. Now what you have to remember, it is always from the North Pole towards the South Pole. So we can draw a line. Let's I'm going to use the green color. So North Pole away, again then towards the South Pole, right? So then after that we can have one line segment this way, arrowhead again away from this North Pole, again one there, away from the North Pole, symmetrically another line segment coming towards, very important, towards the South Pole, right? Again another line is coming towards the south, another line is going away from the north, and then will come to the South Pole. Arrowhead is very important, it's always away from the north towards the south, right? And another one line will be enough, again away from the north towards the south. So we can draw the same 2 lines regarding the bottom side also, that is coming away from the north towards the south, and again this coming this way, away from the north towards the south, right? Okay, so always remember, field lines are going to be from north towards south. That's the one to be remembered, and definitely they're going to check that thing in case they are going to give you a question regarding magnetism, right? Okay, now you can answer. You have to be so confident now, because now you know what's going on behind the screen. Okay, right, so then if we get back to the fact here, so then number 3, they say magnetic field lines provide following information about the magnetic field. Something really important. These lines are not just drawn, they are carrying some information when you look into the magnetic field pattern, right? Or magnetic field diagram, magnetic field lines. So you should be able to reveal these informations, right? Direction of the magnetic field, very important. Now we got to know about that thing in the last the screen, right? While going on the explanation, regarding the last screen, we said we can use plotting compasses. So the needle of the compass is always away, let's say away from the South Pole towards the North Pole. So it is always directed towards the North Pole. What is that? That is what's called this plotting compass, right? So the needle is, that's regarding the what's called this Earth's magnetic field. Anyway, now so if you place let's say, for example, if you place a plotting compass somewhere there here, right, that way, okay, so how that a plotting needle is going to be, it is along the direction of the magnetic field. Needle is going to be that way, right, showing that arrowhead's direction. So therefore that's why we were capable of using plotting magnets to, plotting compasses to get to know about the direction of the magnetic field. Okay, if you place another, let's say, the compass here, plotting compass, the right there, right? Let me take another shape. So somewhere there here, tiny compass, right? Okay, so that one. Okay, fine. It is going to show you the direction of the magnetic field, and will be along that way. The tangent drawn to that magnetic field line at that point. So these are the directions of the magnetic field of the bar magnet. Okay. Now, with that being said, so we can come to the next property. So number one is going to be the direction. So let's say something really important, direction of the magnetic field, and the arrows indicate the direction of the field, as we have already discussed, right? So these arrowheads are going to show the direction of the magnetic field. So it's going to be that way, it's going to be this way, it's going to be that way, and so forth. So just remember, regarding magnets, basically bar magnets in your context, right? Arrowheads are always away from the north poles and towards the south poles. Always away from the north poles towards the south poles. Okay, that's the idea. And that's also going to be one of the important properties. And the next one, strength of the field. Now, strength of the field is something we have already discussed, right? Now, we carried out a simple experiment to get to know about the strength of the magnetic field last time, right? So how we conducted, what was the strategy which was implemented? We got, let's say, steel, iron, steel or iron, whatever, it doesn't matter. So let's say paper clips, right? Usually the steel paper clips, and we just try to have the same separation between the magnet and the paper clips, and we tried. We got to know, or just we observed, how many paper clips can be attracted by a given magnet, maintaining the same separation. So great number of paper clips will be attracted by a given magnet, so that bar magnet was identified to have the greatest magnetic power, right? Or we can say greatest strength. Okay, right. So now the technique we are going to use to represent magnetic field strength by using magnetic field lines is that if we are drawing magnetic field lines closer to each other, since magnetic field lines are kind of piled or they are stacked, right? They are lying very, very, very closer to each other. So that is a place where magnetic field strength is very high. In case you will find a place in the magnetic field pattern where magnetic field lines are they are lying further apart, or they are loosely packed. There's so much space among the magnetic field lines. Come on, that place is having a very weak, or just we can say lesser magnetic field strength. So the fact you have to know is that when field lines are closely packed, or when you draw field lines closer to each other, it should be a place where magnetic field strength is higher, right? So if the magnetic field strength is lesser, right? So we can say magnetic field is weaker. So how you have to draw the lines? So field lines should be, farther apart, or just they should be loosely packed. They should be away from each other. With a certain separation, right? So that's the idea. Lines are closely packed, the field is stronger. Lines are loosely packed, field is weaker. Okay, fine. So that's a particular the factor which has been demonstrated by the last property, this one, right? So here we say where lines are closest something really important, closest together is where the field is strongest, or we can say stronger. Now, if you just, look into this, the field pattern we have drawn, right? So let me use that, probably the red color. Now, this area, what do you say? Lines are relatively closely packed, right? Then some area like this. Now, if you take this area, right? So lines are, what do you say, loosely packed. And if you take this area a little closer to the North Pole, lines are very, very closely packed. So what do you mean by that? Strength at this area, right? So the strength of the magnetic field at this area, let's say area number 1 is much, much greater than to area number 2. So how do you identify that thing? Because we got to know, we can see magnetic field lines are closely packed towards the North Pole in region number 1, and they are loosely packed in region number 2. So loosely packed, meaning lines are having the relatively greater spaces among them, so fine, magnetic field is weaker. And lines are closely packed, or we can say tightly packed. Two lines can be found within a small area. Come on, magnetic field strength is very high. Or we can say just, magnetic field is stronger. Okay, you got the idea, right? So now you have this knowledge with you. We can just, we can see the magnetic field pattern just by using iron fillings or probably by using plotting compasses, right? And then we can draw field lines which are invisible actually, but we can draw them by using pencil or pen, right? On a paper to demonstrate the magnetic field pattern. And at the same time, we can put the arrowheads on top of these line segments we have drawn to illustrate the direction of the magnetic field. Now, another important fact I want you to keep in your mind, right? Probably the last but not the least, the direction of the arrowhead is always from the North Pole towards the South Pole. Just, you have to remember that thing. Okay, so we are ready to, get into the next important fact with that explanation. Now, how to draw a magnetic field pattern, something already we have discussed. So actually, a few additional properties we have to, we have to keep in your mind. Okay, so magnetic field lines never touch each other. Just remember that thing, because these things can be tested, assessed in your examination. So you have to remember, magnetic field lines, they never touch. So if you draw a magnetic field line, let's say for example, if you draw a line segment, one line that way, and you put the arrowhead this way, and probably accidentally you draw another line segment in a way that line touches the blue line, and you're going to put the arrowhead this way. What do you say? This is completely wrong, right? This is completely wrong. Why? Because they never touch each other, right? So therefore, it is not acceptable. So you have to remember that thing, right? Okay. So magnetic field lines never touch. And at the same time, now if you go a little further, they are not allowed to touch. Okay, so we can put another important property by extending that fact a little further. They never cross. Now, for example, if you draw a field line, let's say one magnetic field line that way, and you draw another, the magnetic field line this way, right? So this is completely wrong. This is something which is not going to happen in practice, in nature. So magnetic field lines never cross. Due to reasons which are lying little above the scope of the syllabus, and those things will be explained to you when it comes to the advanced level topics, right? Or probably a little beyond that. But for the time being, just you have to remember, because these properties will be assessed, whether you know about these properties or not, right? So you have to remember these things. You have to keep these properties in your mind. So there is a problem in this place. There, right? So in this area, it seems two magnetic field lines cross each other, which is completely impossible, which is not going to happen, right? So let me write that thing here. This is, okay, these things are impossible. So here they are, and they touching here, those things are impossible. Got it? So never never ever you should try this. Or just, you draw field lines in a way that they either touch or they cross. That is, okay, should be avoided. That should be avoided. Okay, fine. So they never touch and they never cross. And arrows point from North Pole to South Pole of the magnet. Something already we have discussed. Okay, right. So just these two are the additional properties we just got to know about the magnetic field lines, specifically in this particular slide. Okay, so they never touch, they never cross. And at the same time, there's another rule already we got to know. The field lines always start from North Poles and they go towards the South Pole. Or just we can say they end up at South Poles. Okay. Now we can look back to the next important topic, right? With that said, if you go to the next one, these are the few magnetic field lines drawn regarding different the arrangements of the magnets. Here we have in the first case we do have a bar magnet, right? So here is something on you that's going to be a bar magnet, bar type magnet, and here you have U-shaped magnet, or simply we say U magnet. Again, here you have something called electromagnet, about which you are going to talk in a while, right? So it's actually a coil of wire which becomes a magnet once an electric current passes through it. So always what I want you to remember, right? So they are always away from the North Pole towards the South Pole, right? Okay, so and they never touch. Can you find a place where magnetic field lines, these blue line segments, either touch or cross? Never, right? So they, field lines never, number one, touch, number two, cross. Just remember these 2 points, right? They never touch as well as they never cross. That's the idea. Okay, good. So now again, magnetic field lines are symmetrical about the bar magnet. Now, if you take the line of symmetry, for example, let me just take one color to illustrate this point. So this is going to be the line of symmetry, right? So you do have the top side, you do have the bottom side. So top side field pattern and the field pattern of the bottom side, they are symmetrical. If you take this line segment, which is the line of symmetry, and again the top section and the bottom section, they are symmetrical. If you take another line of symmetry, the top side and the bottom side, they are symmetrically drawn. So just remember, if you draw 2 line segments in the top part of the symmetrical line, you have to draw same number of line segments in the bottom side as well, right? Okay, so then we are getting the plunge into one of these important topics. Now we were talking about the bar magnets and almost all types of magnets and magnetic field patterns and their properties, right? Their directions and all. And at the same time, if we can come to know about one of these important facts, like we are actually living, even for the time being, even while the presentation is going on or being recorded, right? So we all are just, kind of immersed in a huge magnetic field. If I say so, are you getting the astonished, surprised? We are immersed in a huge magnetic field. Isn't that so? This is actually the magnetic field of the Earth. So Earth is actually having a magnetic field in its surroundings. So if you place magnet. That magnet is the getting attracted. At the same time, we discussed about the something like this. Now, if you just suspend a bar magnet, right, freely suspended, right, so it is going to get aligned in a particular direction, no matter along what particular orientation you are going to leave that freely suspended bar magnet. It is getting always at a given place. It's always getting aligned a particular direction. So actually, that is the direction of the magnetic field of the Earth. So anyway, we are really, just we were talking about the magnets, bar magnets, and U-type magnets and all, but actually, we are living on the Earth. Earth is, huge magnet. So Earth itself is having a very, very big magnetic field. Now we are going to, it's not good if you are going to leave our section without talking about our own magnetic field, right? We are talking about bar magnets, we are talking about the U magnets, the ring type magnets, platinum magnets, but are we going to leave our own magnetic field? The Earth's magnetic field is not good, it seems like. So we are going to take a little time to get to know about this magnetic field of the Earth. Okay, so magnetic field of the Earth, right? Now, basically, what you're supposed to know is just, we can assume, it's very, very, very important. We can consider the Earth is having a very big, we can say a massive magnet, huge magnet in the core of the Earth. So as shown by this diagram, right? So now here, let's say for example, if I'm going to show that thing by using a color. So here we do have that magnet, right? Hypothetical magnet, right? So okay, so it's going to be something like that, right? So if we can assume there is a magnet within the core of the Earth, in a way that its north pole is towards the downside and its south pole is towards the top side, right? So how you are going to draw the magnetic field pattern regarding that bar magnet? Again, just what do you mean by this bar magnet? It is actually the magnetic field of the Earth. So magnetic field of the Earth can be considered to be produced by a huge bar magnet which is lying in the core of the Earth. So if you have that understanding, so just you can now think about there is a huge magnet, bar magnet inside of the Earth, and you can mark the north pole towards the bottom side of the Earth, and you can mark the south pole towards the top side of the Earth, right, inside the core. And now you can keep drawing very familiar the magnetic field patterns we discussed, we have already discussed, right? Okay, so now you can see these field lines are always away from that north pole of that bar magnet. Very important, north pole of that bar magnet, and again this way and this way, fine. But anyway, due to some the reasons which are lying outside the scope of the syllabus, right? Usually we declare the top side, right, or the side towards the here geographic north pole of the Earth as the magnetic north pole of the Earth. Now you can see there's a kind of correspondence. This is called the geographic north pole, and on the same side we declare, right, for the north pole of the magnetic field of the Earth to be on the same side. So that's called the magnetic north pole. Then we do have the geographic south pole of the Earth, and on the same side we do have the magnetic south pole of the magnetic field of the Earth. So one important thing we have to remember is that geographic north pole and magnetic north pole, they both are going to be on the same side, and geographic south pole and the magnetic south pole, they both are going to be on the same side by declaration, right? Okay, it's a convention we are sticking to, we all are sticking to, right? Okay, so now with that configuration, if we are going to look into the magnetic field lines, right? So if you place the few plotting compasses as we have discussed earlier, right? If you place few plotting compasses here, inside the magnetic field of the Earth, now what would be the direction of the magnetic needles of the compasses? So let me show you by using two arrowheads, right? So here we have, okay, the direction of the compass, and here we have the direction, here we have the direction, and here we have the direction, right? Okay, just one more, here we have the direction, likewise like this. Now these red arrowheads, which are the directions registered by the compasses, right? They are from where to where of the magnetic field of the Earth. That's the question which can be raised in your upcoming paper. So we have to be careful answering that question, right? So now when it comes to Earth's magnetic field, now we have declared the top side is going to be the magnetic north pole, and downside is going to be the magnetic south pole. So all these arrowheads are directed, obviously, come on, towards the north magnetic pole of the magnetic field of the Earth. They are always away from, come on, the south pole of the magnetic field of the Earth. Very important. So that's how you have to, remember that thing, right? So always magnetic field lines are, now you can remember in one of these presentation slides, we discussed about this thing. The magnetic field lines are always away from the North Pole towards the South Pole, right? That's something we discuss about, bar magnets. Now, in this case, we are probably we are finding some kind of the difficulty, but we have to understand that thing really well. We are talking about the magnetic field of the Earth. Now, when it comes to magnetic field of the Earth, magnetic field lines are going to be always starting from the south towards the north. Most probable question they might ask from you is that when you place the compass needle, or just let's say plotting compass in the magnetic field of the Earth, that needle of the plotting compass is directed, come on, question, directed towards the north pole of the magnetic field of the Earth or directed towards the south pole of the magnetic field of the Earth? What is your answer? We are talking about the magnetic field of the Earth. So therefore, remember, come on, yeah, magnetic field of the Earth. So therefore, compass needle is always directed towards the north magnetic pole of the Earth. Right? Just remember that way. So therefore, automatically you can remember, the plotting compasses are directed away or getting aligned away from the south pole of the, or just south magnetic pole of the Earth's magnetic field. Okay, so just if we recap what we have learned here, right? So just by the two facts. So compass needle, we can just say compass needle, the directs, or we can say points towards the north pole of the magnetic field of the Earth. Very, very, very important, right? So we are talking about the magnetic field of the Earth. That's the most important fact. So in that case, the what's called this compass needle, or just say the direction of the compass is going to be towards the north pole of the magnetic field of the Earth. That's the one you have to remember. So that thing is going to remind you automatically. The compass is always directed away from the south pole, away from the south pole of the magnetic field of the Earth. Right. So that's all about that, and then we can just look into these the figures, so we can learn a bit more about these magnetic field patterns. Right now, what do you think? Here we do have the bar magnet. So regarding the bar magnet, we do have the north pole here. Regarding the bar magnet, we do have the south pole there. So we can draw the lines, right? Regarding the bar magnet, we can draw the lines away from the north pole towards the south, and so forth, right? But we know we have declared that point to be the very, very, very important magnetic north pole, and we have declared that point to be the magnetic south pole, right? So regarding the Earth's magnetic field, which means, come on, or just in which case south pole is going to be the bottom one and the north pole is going to be the top one. Now you can compare the directions of the magnetic field lines. So regarding the Earth's magnetic field lines are away from the south pole and towards the north pole. Did you get that? Regarding the Earth's magnetic field, right? So regarding the Earth's magnetic field, again, field lines are away from the south pole. Very important. Away from the south pole, and towards the north pole. Okay, that's right. So now I want you to make the distinction between the poles of the bar magnet and our declaration. Conventionally what we have declared. Okay, so top side, it is going to be the magnetic north pole of the magnetic field of the Earth, and bottom side is going to be the magnetic south pole of the magnetic field of the Earth. Okay, so if you are going to talk about the magnetic field of the Earth, then always magnetic field lines are towards the north pole of the magnetic field of the Earth, right? So just remember that thing in that way without making any confusion. Okay, right. Now if you can just okay, look into the right side figure, the figure which is lying on the right. Again, it resembles the idea. So we do have the regarding the bar magnet, we do have the south pole and towards the top side, and the north pole towards the bottom side, right? But we're gonna again declare the magnetic north pole to be on the same side as that of the geographic north pole, and we're gonna declare the magnetic south pole to be on the same side as that of the geographic south pole. Actually, they match. It's easy to remember and easy to deal with. We do have the geographic north pole on the top side, and therefore we can say the magnetic north pole also. Geographic south pole towards the bottom side, so we do have the magnetic south pole on the same side, so that we can remember the what's called this how the poles are going to be regarding the magnetic field of the Earth. So then now field lines, the direction of the field lines can be remembered easily. So they are always from the magnetic south pole of the Earth's magnetic field and towards the magnetic north pole of the magnetic field of the Earth. So that's how things are going to be. So you can just go through these figures. They are nicely, so clearly representing these differences and conventions and the directions of the field lines. Okay. Right. Now, there's a small question now they're asking regarding this magnetic field of the Earth. Why the imaginary magnet inside the Earth is shown with a south pole at the top, which means the North Pole. I mean, come on, yeah. So now a compass needle will point towards the Earth's magnetic North Pole, which is in the Arctic, near to the geographic North Pole. That's how you have to remember that thing, right? So that's the easiest way to get that thing done. So we have the magnetic North Pole and geographic North Pole on the same side, right? Okay. So therefore, we do have let's say somewhere there here, we do have the magnetic South Pole, and let's say towards the Arctic side, we do have the magnetic North Pole, and then we have that hypothetical magnet somewhere there, from here to somewhere there here, right? So we can have that hypothetical magnet, and then we can mark the poles of the bar magnet. It is going to be the South Pole here, it's going to be the North Pole there. Now we can draw the field lines. So if I just draw few just for the illustrations, right? So it's going to be something like that. They go this way, and we can draw few more lines just for the. Okay, so they come that way all the way up to here, and they go this way all the way to there, right? So now how we are going to mark the directions is always away from the North Pole of the bar magnet and towards the North Pole of the South Pole of the bar magnet. But when it comes to the Earth's, right? So let me use a different color for that, right? So now in this case, I'm going to take this circle and I'm going to place it somewhere there here, right? Okay. Let's say that's going to be the Earth. So that's the Earth. So now we are going to talk about the magnetic field of the Earth in particular, right? So now, what about the direction of the magnetic field line regarding the magnetic field of the Earth? It is from the magnetic South Pole, from the magnetic South Pole towards the magnetic North Pole, right? So again, if you place a compass here, so direction of the compass is going to be always towards the North Pole of the magnetic field of the Earth. That's what you have to remember. I mean, something really, really important, and something which has a very, very big chance to appear in your question papers, right? Okay, so just remember that thing in that way. Something really, really important regarding the Earth's magnetic field. It's actually two important facts. Number one, it's regarding the bar magnet. Magnetic field is from the North Pole towards the South Pole. There are no changes. We discussed about that thing, a while ago. Regarding the Earth's magnetic field, due to our declarations for the magnetic South Pole to be on the same side as that of the geographic South Pole, and magnetic North Pole to be on the same side as that of the geographic North Pole, right? So these are the declarations, conventions we are using. So according to these the conventions, right? So magnetic field lines are going to be from the magnetic South Pole towards the magnetic North Pole of the Earth. So the second important fact you have to remember, right? To answer accurately in your paper is that regarding the Earth's magnetic field lines are always towards the magnetic North Pole of the Earth. That's the idea. Okay, fine. So now we can get into one of the important topics. Now it is something like this. We talked about the Arctic area, I mean, where we do have the geographic North Pole as well as the magnetic North Pole, right? So at the same time, we do have the geographic South Pole as well as the magnetic South Pole towards the Antarctic area. So now, the Putana, sometimes you may have not seen these things, but probably through the internet or in television, right? You may have seen these the figures or sometimes videos so many times. Now, the time periods are there. I mean, during the year, right? So we will be able to observe very intense light beams, very intense large light beams, very illuminated areas towards the North Pole of the Earth and the South Pole of the Earth as well. Now, actually, these the lights, illuminated intense light beams, right? The taking place towards the what's called this North Pole is called northern lights. So these illuminations taking place towards the South Pole, right? Are called the southern lights. North Pole, northern lights; South Pole, southern lights. Sometimes these illuminations or light beams, the glowing, right, or illuminating the North Pole, are sometimes called aurora borealis, right? The light beams towards the South Pole are sometimes referred to as aurora the australis. That's simply because of the Australia lying a little towards the South Pole of the Earth. Anyway, so now what I wanted to illustrate by using this particular slide and the scenario, right, this particular phenomenon, is that all these things, all these illuminations are consequences of the magnetic field of the Earth. Right? I'm surprised. What do you say? I mean, actually, it is because of the magnetic field of the Earth. So people who are living, in case you have cousins or some relatives towards the countries the little closer to the Arctic area, and right, probably they have this experience. It's a very nice experience. So you can ask from them, right? So how it looks and the time periods, they can see these things very clearly. So Maputana, actually, we don't have to talk about these things in detail because we need a little more knowledge, the lying little beyond the scope of your context, right? But just I wanted you to come to know all these natural phenomena are occurring because of the magnetic field of the Earth, right? So magnetic field of the Earth is capable of just trapping or just the holding charged particles like the protons, electrons, like charged particles inside the magnetic field of the Earth. Now, these trapped particles, now for example, let's say you are trapped inside a room, you and your brother and a few of your cousins, you all are trapped inside a room, right? So probably you are getting excited and then you keep going here and there inside the room. It's a very relatively the small area, so you're gonna collide, right? You're gonna make impacts. So in a similar manner, these trapped charged particles, while they are moving here and there inside the magnetic field of the Earth towards the North Pole as well as towards the South Pole, right? These charged particles are going to make huge number of collisions. So due to these collisions, these illuminations are produced, right? So details will be discussed a little later. Like when it comes to, the let's say either in one of your sections in your advanced level, right? So I'm going to reveal all the details regarding the particles, the charged particles in a magnetic field, right? Okay, so it's going to be a topic which is not relevant at this point. Anyway, so have this experience. I mean, like, there are so many things in our nature we can observe due to, or just, as a result of our own magnetic field, right? Our own magnetic field in which we are living right now. Okay, so now the figure shows you beautiful display of light in the sky, which is known as the northern lights. Northern lights was the north pole of the Earth, which is also known as the aurora borealis, and it occurs when charged particles streaming from sun, meaning particles are getting out of the sun or repelled, right? The particles escape from the sun, become trapped by the Earth's magnetic field. So Earth's magnetic field is the one which is responsible for all these glowing, beautiful illuminations. See how, this magnetic field is kind of important. Okay, right. So now I just wanted to, come to this point. We talked about the magnetic materials, and we just, got to know that the steel as well as iron, steel, right? They are, readily found very strong magnetic materials in our surroundings. But now steel is not, by composition, steel is not 100% iron. Instead, steel is by most of the steel is by iron, and a small percentage of carbon is also added to that iron, right, in order to obtain few important properties of the steel. So steel is actually developed iron, we can say that way. Steel is developed version of iron, right, by adding few amount of or just we can say a small percentage of carbon. So iron plus carbon is steel. Now why we did so? Steel is having some advanced properties than possessed by iron. So iron sometimes cannot be used because iron do not, or iron pieces of iron do not possess these properties, right? But due to the addition of carbon, the steel is going to have those developed properties. So that's a major difference between iron and steel in composition. Okay, that's the idea. Now, if we take the magnetic properties, now how iron and steel are going to just behave regarding the magnetism is something like this. Iron is also a magnetic material, and steel is also a magnetic material, very, very strong magnetic materials. Now, iron can become a magnet very easily, as well as it can lose magnetism relatively easily, right? Whereas steel can become a magnet, not that easy, right, as that of the iron, as well as once that steel has become into a magnet, that magnetism lasts long, right, or we can say last for longer time periods than to that of iron, right? So basically iron can be, we say, magnetized relatively easily. Steel, the hardly can be made a magnet, little harder to make it a magnet, but once magnetized, that magnetism prevails for longer time periods than that of irons. Okay, so is of iron. So now regarding iron, what we can say, just the easily magnetized. Now always, now this, when I say easily, it is always relative to steel. That fact should be remembered, right? Or just, you have to bear that thing in your mind. Always I'm comparing the iron and steel, not all materials. Here specifically we are talking about iron and steel. So iron can be easily magnetized, can be magnetized, right? Okay, and when it comes to steel, it's a little difficult, right? So it takes time, or we can say the relatively difficult. Relatively difficult to magnetize. That's the nature of the steel. But now once magnetized, now for example, by using this bar magnet, the top side, the big bar magnet. So this iron, the rod, has become a magnet and steel as well, right? So now what you can see, I mean, once we sprinkle the iron fillings in the surroundings of these two bars, I mean iron bar and the steel bar, most of the iron fillings are getting stick to the poles of the iron than to that of the poles of the steel. Now what this means to you, iron has become much stronger magnet than to that of the steel. Did you get that? And that's why it is attracting great number of the iron fillings. Like the experiment we conducted and we compared the strength. Greater number of iron, greater number of paper clips will be attracted by a given magnet with the certain separation, right? So that magnet is going to have greater magnetic power, or we can say that magnet is much stronger than the other. So likewise, now here, more iron fillings are attracted by the iron, the bar than to that of the steel. So thereby we can decide iron is strongly magnetized than to that of the steel, right? At the same time now, once that part is done, so we're going to remove that bar magnet. We're going to remove that bar magnet, right? We're going to take that bar magnet away from the iron rod and the steel rod. So now iron and steel is left alone. In that case, what's going to happen is obvious. Almost all the iron fillings, right, which got attracted to the iron, is going to fall off. They're going to go away, right? They're going to fall. Why? Because iron has lost its magnetism. Iron is not a magnet any longer in this case. So we can say that iron is not a magnet any longer. That's how it's going to be once that bar magnet is removed. But you know what? I mean, probably for your surprise, right? That steel, what got attracted to the steel, I mean the amount of iron fillings, they stay almost same. Almost same amount of iron fillings stay. I mean sticking to the steel, the bar, which means that steel has become a permanent magnet, right? Okay, so another important difference between steel and iron is that once magnetized, so that the magnetism prevails, it lasts long regarding steel, right? And iron might lose its magnetism very easily, but steel does not. Steel is going to prevail its magnetism for longer time periods. Okay, right? So that's the difference, right, between iron and steel. Now again, I want you to remember, steel is also a form of iron, and you can better say this way: steel is a developed version of iron, right? So let me write that part here for your information. So something very important: steel is a developed version of, you can say, iron. So basically what it is, just steel, right, is equal to basically iron plus small percentage of carbon. That's it. Oh, fine. So you get the idea about that thing. So now we can focus on the next slide. Now we are coming back to the second part of the presentation, right? At the beginning we just classified magnets into permanent magnets and electromagnets basically. Now we are going to talk about the electromagnets. What are electromagnets and how we can make electromagnets and so forth. So details regarding the electromagnets, right? Okay. So basically, how to make the electromagnet stronger. Now, electromagnet is just a coil of wire, as you can see in this screen, right? It's a coil of wire. So if I just take this one, this is also something we have already come across from our early ages, right? And it is just the coil, right? This coil. Okay, so we can say coil of wire, well, is the electromagnet, and usually we are using some kind of the core, right? So usually we are using some kind of core which is made out of iron. Sometimes we say soft iron, right? Some metallic the core, something like cylinder, right? Or it can be some kind of rectangular the pipe or something, right? It doesn't matter. The shape of the cross section is not very important, but usually we are using a pipe like thing, right? So let's say it's a metal pipe. So we are using that kind of core to make that magnetic field, the strength of the magnetic field of the electromagnet much stronger. And we are going to reveal much more details regarding that a little later. Right? For the time being, just coil of wire is going to be the electromagnet, and usual practice is to wrap that regular wire into a coil around a substance called, actually a metallic substance called core. Right, so just we can show this thing, this cylinder-like thing, right? That pipe-like thing is called the core. It's better to write metallic core. Or sometimes we can say it is the soft iron core. Right. So now soft iron is a special type of material which is highly capable of enhancing the strength of the magnetic field of the electromagnet. Okay. Now here in the second figure we can see we do have the coil here, right? And it is supplied with an electric current. We can say electric current I by using a battery. Right. Now in this figure we do have so many windings, ample number of windings, so that we can enhance the strength of the magnetic field, right? And here we do have the supply, and here we have the electric supply. So this is the incoming current, that's the outgoing current. And this diagram shows the what's called this right hand side bottommost corner, this one, right? This diagram shows the poles of the electromagnet. If I just draw a small, let's say a rectangle like thing like that. Okay, now what you can visualize, what you can do is to visualize this coil to be a bar magnet, right? Okay, so now you can visualize this one to be a bar magnet. So let's take that thing and put that thing by using an arrowhead, right? So that one can be visualized, right? So now that electromagnet can be considered to be a bar magnet. Right. So that's the most most important part there. Now, if it is a bar magnet, its magnetic field pattern, should resemble, right, the magnetic field pattern of a real bar magnet. What do you think about that? Now, yes, of course, yes, it is working exactly the same way. Now, here we have the North Pole, and here we have the South Pole. So now you can see field lines are flowing away from the South Pole and towards the North Pole. Maybe South Pole. Again, away from the North Pole towards the South Pole. Always away from the North Pole towards the South Pole, right? And we do have lines like that, and we do have lines like this, and so forth. So you know about the magnetic field pattern of the bar magnet, right? So very, very, the easy way of figuring out the magnetic field pattern of an electromagnet is to consider that electromagnet to be a bar magnet. Just inside your mind's eye, replace that coil which is carrying an electric current by a bar magnet. So outside field is going to be identical. Field lines are going to be always away from the North Pole towards the South Pole. Or the particular end from which field lines are coming out is going to be the North Pole, and the end into which field lines are getting closer or the approaching or probably getting absorbed is the South Pole of the electromagnet. Right, okay. So now just tiny small the description regarding that one. And now again we do have the same question as we got with the permanent magnets, right? How we can make electromagnets, to have a significantly greater the magnetic field strengths, because sometimes in industry we don't want weak electromagnets, we need very powerful electromagnets. So how we can make that magnetic field strength or the magnetic power of an electromagnet greater? How we can enhance the power of an electromagnet, right? Okay. So this can be done by using several the methods or by using several techniques. Now, basically an electromagnet is a coil of wire. So just we should be able to understand probably that coil is going to be something like this. Let's say a short coil, or that coil is going to be something like that, which is going to be a relatively longer coil. Now, obviously, let's say coil number 1, just for the sake of addressing, and coil number 2. Now, what do you think? What you feel by nature? What do you feel intuitively? You can say, naturally, you can say, coil number 2 should have, greater strength. Obviously, why? Because it is having more turns of wire. So therefore, it is going to be much stronger. So one of the very dominant way of making an electromagnet stronger is to increase the number of turns of the wire. See, he's going to be 50. Here we do have 100 turns. Here we have 150. Here we have 200 turns. So number of turns, right, can be, increased. So if we can make let's say coil of wire with let's say 300 turns, 500 turns, thousands many turns, they are going to be much stronger than all the electromagnets. So therefore let's say one of the techniques is going to be increasing the number of turns, and another one is to use a core material. Now usually we use soft iron due to reasons which are lying a little beyond the scope of the syllabus, but for the time being, just you can write soft iron, right, or probably mu metal or permalloy like materials. But soft iron is the most commonly, or we can say readily available material, right, and most frequently used material as a core. So now, rather than using that the coil in isolation, alone, we are going to use some core. So which will help the coil to concentrate its magnetic field, or just we can say its magnetism, so thereby producing the stronger magnetic field. So another method, now let's say number one, another method of increasing the field strength of an electromagnet is to use a soft iron core. Or just you can simply write iron core, but I highly recommend, right, to write soft iron core, because examiners will get kind of like, impressed with your answers. Okay, this candidate knows about the core material very accurately, and he or she is aware about most frequently used the core materials, right? So it's not just iron. I mean, it is going to be soft iron due to the some reasons you will learn about in advanced level or little beyond that. Okay, fine. So just write using a soft iron core, right? Is going to increase the magnetic field strength. And another important fact, probably we're gonna mark that thing as number 3, but actually, I mean, numbers are not going to show the priority, right? I mean, they are just, for the sake of addressing. Now let's say electromagnet is just because of an electric current. Now you take the coil of wire. It is simply a mere coil of wire. That's all. It's just a coil, right? It is not a magnet, or it has no other special properties. It's just a coil. That's all. But once supplied with electricity only, it is going to gain this magnetism, or it is going to become a magnet. So electric current is the one which is going to convert that let's say mere coil into an electromagnet. So therefore, what if you supply a greater current, or we can say larger electric current? Larger current is the reason which is why that coil became an electromagnet or gains the magnetism, right? So if you use a larger current, what will happen? That coil will become a stronger magnet. That's the idea, right? Okay, so you can increase the electric current flowing through the coil of wire, so that strength of the magnetic field of the electromagnet is going to go up. So Maputala, there are, basically there are the 3 main techniques as we have illustrated here, right? By which we can increase the strength of the magnetism of an electromagnet. So we can say, one of them is going to be to increase the number of turns or number of, let's say, coils, right? So number of turns of the coil. And number 2, so we can just, use a soft iron core. That's going to be number 2. Fact number 3, probably the last but not the least, again, right? So supplying a greater current, or we can say larger current, is also going to increase the strength of the electromagnet significantly. Okay, so those are the main methods by which we can increase the strength of the magnetic field of an electromagnet. Now, in this the top figure, they say increasing the strength of an electromagnet, and they have specified something. We better take that thing into consideration. They have specified number of batteries. Now, what we are going to do by increasing number of batteries is to, increase the current, right? So batteries are connected in such a way that, it's very important, batteries are connected in such a way that, the electric current passing through the coil is going to increase. So in order to do that, batteries should be connected, end to end. Got it? That kind of connection is called a series connection, which is not relevant at this age. It's called series connection or series configuration. You'll be able to learn about these things in detail when it comes to advanced level, right? So you have one battery here, okay, like that, and you have to connect the other battery, okay, this manner. So it's called end to end. So the other battery this way, right? That's called series connection. So easily you can remember end to end connection, end to end connection, right? Or at the same time you can remember head to tail connection. Right, okay, so you can use one of these two, strings while you're writing your answers. Head to tail connection or is end to end connection. So therefore by increasing the number of batteries, what we are anticipating, actually we are expecting to increase or supply a larger current. So by supplying a larger current, we can increase the strength of the magnetic field of the electromagnet. So practically how we are going to increase the electric current? Just by using larger number of batteries or by increasing the number of batteries, right? Okay, that's going to be one practical way of increasing the electric current, by increasing the number of batteries. And another way of increasing the electric current passing through the coil is to connect the ends of the coil to something called a variable power supply. Something called a variable power supply. Which is basically an equipment which is capable of supplying currents, right? So let's say that way, basically supplying currents, right? Okay, it is connected to that one, and this end is connected to that side, right? So the purpose of the variable power supply, and details about variable power supply is not relevant at this point again, and just you have to get to know the purpose of the variable power supply. It is capable of, as by its own name, variable, it is capable of supplying the varying current, fluctuating current. You can increase the current, you can decrease the current. So in case you have a variable power supply available in your laboratory, so you can ask for that thing with the assistance of one of these instructors available, right? And then there's a knob. Okay, you can turn that knob in a way that the current which is going to pass through the coil is going to increase, thereby increasing the strength of the magnetic field of the electromagnet. So basically, there are two practical ways to increase the electric current, to make the electric current a little larger, right? To make the strength be bigger or greater. So one of the most frequently used method is going to be increasing the number of batteries, and number two, by using a variable power supply. Okay, so that's how we are going to increase first of all this the strength of the magnetic field of an electric the magnet, or just we say electromagnet. Or simply we can say how we can make a given the electromagnet into a stronger electromagnet, right? So by using these methods. Okay, fine. With that one, we are ready to get into the next one. So just that's going to be the summary, the things we discussed already, right? Putting into one point. So we can say just the consolidation of our discussion so far, right? So that's going to be number one, make a bigger electric current flow through the coil by either increasing the number of batteries. That's a method, right? So number of batteries, increasing the number of batteries is going to be the practical way. So we can say practically what we can do. Practically what is done is this, right? So we are going to increase the number of batteries. That's what we are going to do in practice. So what we are going to expect by doing so is to supply a larger current. Okay, so next one is going to be using low resistance wire. Now, what do you mean by low resistance wire? It is something like this. Now, in case, you know, the wire which is used to make the coil is going to have the too much opposition for the electric current, then not only the electric current, what about you? Somebody is having so much opposition on you. You try to stick to that person, or you try to avoid that. What do you say? Simple answer, you try to avoid. What do you say? I mean, like, you know, I'm also going to do the same thing. So we all, right? So that's the idea. So in case that coil, I mean, the material of the coil is going to show some greater opposition for the electric current, then electric current is going to be, relatively smaller. But in case we are using a material, the material to form the coil, right? And that material is showing only a relatively lesser resistance for the electric current. So then what about the electric current which is going to flow through the coil is going to be relatively larger. So therefore, you can use low resistance wire, or just, I mean, you can say, I mean, high conducting material, right? So that material which is used to make the coil is highly conductive. Right, so you can just write low resistance wire. So therefore, it allows high currents. Okay, when the wire is made up of low resistance material, the electric current for a given number of batteries increases, and thereby making the magnetic field stronger. Now, what's going to happen? The electric current will be raised, okay, increases, thereby making the magnetic field stronger. That's what which is going to happen when you're going to use some low resistance, you know, the wire or material to make a coil. Right, fine. So that's going to be like, you know, those are the ways, I mean, methods we are, or probably things we're going to do in practice to make the current greater. Okay. And next we can, I mean, look into the second factor we just discussed, right? So make the coil with more turns of wire. So make the number of turns greater as possible, like we discussed already. So 50, then 50. With 100 we can get more strength for the same current, and with 150 we can have even greater strength, and greatest strength will be with 200 turns for the same current, right? So we can increase the number of turns, so thereby increasing the strength of the magnetic field of the electromagnet. Okay, so number 3, I mean, something again we have already taken into account, that particular one. So I have already illustrated that one. This particular substance, or let's say just the cylinder, is called the just we can say is the core material, right? And usually we are using, as you know already, soft iron, and we can use that word, soft iron core. All right, now what is going to happen is this. Now when you supply, let's say when you supply an electric current, let's say it is coming up along this way, it is coming that way, right? So it's a little bigger. All right, okay, so well, it is coming, the current is coming along that way, and current is leaving the coil along that terminal. Now current keeps going through these, and then coming this way, and going that way, going this way, getting all the way that way, getting all the way this way, and going and coming back, and so forth, right? So current keeps flowing this way, and going to go going to leave the coil, I mean, to that final terminal. Now electric current is going to produce the magnetic field of the electromagnet, that coil. But that electric current produced magnetic field is kind of, we can say, distributed, or we can say kind of the scattered. That's the best word. Now, Putala, you have this idea with your, the subject. Now, what do you mean by, now for example, let's say you have a color, right? You're gonna paint something and you're gonna apply the strokes all over the page, right? And at different places without using the brush at the same place, right? So you keep drawing all over the page at different places. So what about the thickness of the stroke or the depth of the color? Is going to be very low, very low, right? Instead, if you keep drawing on the same line segment, if you keep painting on the same spot, so what about the thickness of the, or the weight of the line drawn, or the depth of the color painted? What do you say? It's going to be very high, right? So same thing is going to happen in this case also. So in case you don't have the soft iron core, the magnetism is there. There is a magnetic field associated with this electromagnet, the coil of wire, right? So with the electric current. But that magnetic field is a little bit scattered, or we can say it is kind of like, distributed all over. So therefore, what about the magnetic field strength of the so produced magnetic field? Is going to be relatively low. Why? Because it is scattered, right? Now, it is kind of like, we can say, magnetic field is a little bit diluted, something like that, right? So all what is done by this, by introducing this soft iron core, is that soft iron core is going to concentrate, or it is going to take all these, the distributed magnetic field as close as possible, right? So basically, it is going to concentrate. It is going to make that magnetic field kind of concentrated. Now, when the magnetic field, when that spread, or just, distributed magnetic field is made kind of concentrated, so what will happen to the strength of the magnetic field? It is going to go up. So that's the way, that soft iron core is going to work. Now, actually, because of this electric current which is flowing through the coil, that soft iron core is getting magnetized, right? So it is getting magnetized, and it is going to support, or it is going to arrange the magnetic field of the coil, with it, by making that magnetic field a little more concentrated. So thereby increasing the strength of the magnetic field. Now, if you go through the statement given, when the wire is wrapped around an iron core, that iron core is magnetized. One important point you should write in case they will give that thing in your paper. That iron core is magnetized. That part is very important. That iron core is getting magnetized as the electric current passes through the coil. This is because iron is a magnetic material, of course. Not only iron, but about the steel, yes. This increases the strength of the magnetic field of the magnet. So just you have to write the iron core is getting magnetized, and that magnetized iron core is going to concentrate the magnetic field of the coil, thereby increasing the strength of the electromagnet. Okay, right, fine. So that's how you're going to answer in case they will ask a question regarding the purpose of the magnetic core, or just, we can say the iron core. What is being served by the iron core? supply and co, right? You can now write the answer accurately. Okay, so thereby you're scoring high marks. That's the target, right? Okay, now with that one we can get into the next one, the magnetic field pattern of an electromagnet. Now what do you think? Now this is something we have already discussed, and I told you, just in this case, assume you have a bar magnet, right? Okay, enclosing that coil. Now in that case, you can identify, okay, now the field lines are coming out from this end, so therefore that is going to be the north pole. Field lines are absorbed, or field lines approach, right, to this end, so therefore that's going to be the south pole. Got it? So that is what is shown in this left hand side bottommost corner figure. So if you're going to resemble that or replace that let's say coil by using a bar magnet, so what you're going to get is exactly, field pattern is going to be the almost identical to what was produced by that electromagnet, right? Okay, so and then the things we discussed, field lines are flowing away from the north pole towards the south pole. Exactly the same thing, right? Field lines they are flowing away from the north pole, and they are getting absorbed by the south pole. Okay, now magnetic field lines come out of one end of the electromagnet. That end is called the north pole, of course. Yes, we know that. And the field lines go round back into the other end, and that end is called the south pole, right? That's all about that. Okay, fine. Now the magnetic field of an electromagnet is like the field of a bar magnet, something I have already suggested, right? Now if you are given with that electromagnet, just regarding the outside field, right? So just think about that electromagnet in terms of bar magnet. So that you are so damn capable of drawing all these field patterns and identifying the poles very, very accurately and so forth, right? So now again, field lines are coming out of the south pole, field lines are going in towards the north pole, the south pole. Field lines are coming out of the north pole, and field lines are going into the south pole, and so forth, like so. That's what. So always remember regarding this outside field, right? So something important regarding the outside magnetic field. Regarding the outside magnetic field, right? So you can always replace the electromagnet, the coil of wire, by using a normal, well-known bar magnet, right? Okay. Now, with that we are coming towards the latter part of the presentation. Now we talked about the permanent magnets, we talked about the electromagnets, we talked about the magnetic materials and metallic magnetic materials, metallic non-magnetic materials, and non-metallic, the non-magnetic materials, and how to make magnetic fields, how to make magnets, thereby magnetic fields, and how to make the magnetic field stronger, what are the techniques we can use. Regarding electromagnets, how we can make the electromagnet, and how we can increase the strength, right? All these facts have been thoroughly discussed with all bells and whistles, okay? Within the scope of the syllabus, within the context. Now we are doing something. Now why we do have all of this science, right? All the science, magnets and magnets and the other branches of physics, to make the life easier, to make things which can make our lives easier. Now we are at that point. Now we talked about the magnets and all. Now we can do something with the magnets, right? Now we are about to discuss, about the things which can be produced by using our knowledge on magnets, right? And the things which can make our lives easier. So that's going to be the uses of magnets. Now usually when it comes to like the gadgets or devices, right, which are using magnets in day-to-day life, most of them are using electromagnets. Now, one of the very main reasons why we are usually sticking to electromagnets when it comes to the day-to-day life is that, now I could have mentioned this reason previously while we were discussing about the electromagnets in particular, but I wanted to mention that fact here because I think this is a place where it comes so handy, right? Okay, so now the very main reason why we are going to use let's answer question and then I quickly answer, right? Why we are going to stick to electromagnets? Why electromagnets? Electromagnets in almost all practical applications. Almost all practical applications. The big question, right? Why electromagnets? Electromagnets are dominating over permanent magnets when it comes to the practical applications. The very main reason is that, probably it's obvious to you, right? Now, permanent magnets, once used, once assembled in whatever the gadget or the device, it remains magnetized for long time periods. Probably that instrument is not being used, right? Like, let's say, one of the examples shown in this, let's say, for example, a motor, right? Now, here you have a motor, right? Here, and you have a generator here. So let's say generators are not used 24/7, right? Usually they are used when there are power cuts. So during that, during the time intervals, we have power from the electricity board. There is no special need of using generators unless otherwise we have a specific purpose, right? So therefore, these generators can be, kept switched off. But in case now that we are using, let's say, permanent magnets inside the generators, what's going to happen? Now, these magnets or motors, these magnets are always in a state of switched on, it seems. Why? Because permanent magnets are always, magnets. They remain as magnets, right? The advantages of the electromagnets, one of the very main advantages of the electromagnets over permanent magnets is that when we supply electric current, so that electromagnet becomes a magnet, right? So when we cut off the supply, when we cut off the electric current, when we switched off the electric current, right? So that electromagnetism or the magnetism of the electromagnet vanishes, disappear. So then after that, it is going to be just merely a coil, right? Or piece of, just we can say a piece of iron or probably a piece of wire, right? Just a piece of material. So that material, is resting there until it is required to become the magnet. So whenever we need that coil to become an electromagnet, we can supply the electricity so that we can make use of that, right? Okay, so that's the idea. So therefore, now the very main reason, why electromagnets in almost all practical applications, right? So they can be switched on and switched off, right? Okay, so that's the idea. So now we can say electromagnets, that's the answer. So electromagnets can be switched on and off on our requirement. or just we can say whenever needed, right? So basically we can say just so we can say switch it on and off when required. Right, that's going to be the main reason, right? So something you have to remember, the one of the main advantages of the electromagnets over permanent magnets. Let me write that thing as well, right? Because they might test this fact in your paper. Okay, so one of the main advantages of electromagnets over permanent magnets. Whoa, that's a very important fact. Okay, that's going to be one of the very main advantages of the electromagnets, right, over permanent magnets. Fine, can be switched on and switched off whenever, come on, the requirement is there. So whenever we need, we can switch on. So therefore it starts to function as a magnet, and once done, we can cut off the power supply, electricity, so that it goes off, right? So yes, we can leave that thing aside, this area. Okay, so probably it saves more power and be very useful, because we can switch on and switch off the as we want. Okay, so now if we just get back to the topic of the users. Now we got to know why they are going to use these electromagnets on frequent basis, right? So we do have in users, right, among the many apparatus we're going to use in our day-to-day life, right, in which electromagnets or we can say generally magnets are used. Now electric motors, they at the heart of their function, we do have the magnetism. So small scale motors are there, very small motors probably you have seen, right? So these small motors, they use permanent magnets, but very large magnets are also there, right? Like generators, right? So in generators, we are not usually using permanent magnets. Instead, we are using electromagnets. So the motors and generators, actually they are like the two sides of the same coin. Now what I meant by saying two sides of the same coin is this. Now a motor, if you want, can be used as a generator, right? And vice versa. A generator, right, can be used as a motor as well. So it is just depending on the fact that whether we are supplying the power, meaning we are supplying the current, or we are going to obtain the current or the power, right? Okay, so we don't want to discuss about the details right now, but just remember, motors and generators, they are actually internally having the almost same structure, right? Anyway, they both demand the electromagnets in order for them to function properly. And another one important, the usage, the application, right? Something you have already gone through, doorbells. Actually it's a bell, and it is also something which is going to use the electromagnet. So there's a small hammer. So when we supply the current electricity, so that coil is getting magnetized, so that hammer is attracted towards the bell, right? So that the bell is going to make a sound, and then current supply is the cut off, then that hammer is released, so that sound is gone, again magnetized, then again sound is produced, and so forth. Like this is done several times a second, so that we can hear that bell is sounding. So that's how it's going to work. And another important the application is something called a relay, right? This is something another important actually a switch. So we can say it's a switch, right? Relay is basically a switch. Now you might say, okay, fine. If it is a switch, we could have used the normal switch instead of or in place of a relay. I mean, the main difference between a normal switch and a relay is that a relay can switch on and switch off so rapidly. I mean, at a very higher rate than to that of a normal switch. Now, normal switch, which is operated by a human being. Let's say you go and switch on and switch off, switch on, switch off, switch on, switch on. I mean, how many times you can do that? Let's say in a second, probably maximum 2-3 times. What is it? Not more than that, right? But relays can be switched on and off probably thousands many times just in 1 second. Did you get that? Did you hear that? Thousands many times just within 1 second. So relays are in speed concerns, right? In speed concerns, relays are way ahead than normal switches. So that's the very main thing. Okay, so now you can see inside that relay, right? So just wanted to show you that thing. Inside that relay, you can see there's a coil here, right? You can see there's a coil. So obviously now when you see a coil, you can understand, oh, we are going to supply some electricity. So that electricity keeps going through the coils. So it is going to become an electromagnet. So of course, yes, that's going to be the electromagnet. So let me write that part for you. So it's going to be the electromagnet. If you were able to guess that thing, okay, this coil should be an electromagnet. That's perfectly all right. Okay, so we can say that's the electromagnet, right? Okay. So that's about that. This is the electromagnet. Now, what do you think about the inside of that? The turns. Probably we do have the core, soft iron core, right? Which is going to increase the strength of the electromagnet. Okay, that's about the let's call this relay. So now just what I want you to remember to be ahead than your colleagues is that it is also functioning as a switch, but with very, very, very high speed, right? So speed wise, relay is going to be way, way ahead than a normal switch, very high speed. So we can say very high speed, right? Okay. Switching on and off can be done at a very, very high speed. That's the main difference between the normal switch and a relay. Okay. Now the other one is going to be something known to you probably from your small ages. Probably you did some, you made some models for exhibitions in school, right? Science exhibition and so forth. Okay, so magnetic cranes. Now this is also basically the functions depending on an electromagnet, right? Here we do have that electromagnet there. So when the operator is going to supply the current, so it becomes a very strong electromagnet. So which is going to attract magnetic materials, right? So now we have discussed about that thing, like nothing. So all these magnetic materials will be attracted, like iron, steel, debris, right? All these cobalt stuff, right? Those things will be, most of them are going to be by iron. So all these the things will be, scraps will be attracted by that strong electromagnet, so that the operator can take that arm, rotate that arm, right? To some let's say a truck or something like that, right? So that arm can be rotated to a different place, and then electric supply can be cut off by the operator, so that electromagnetism is gone. So there is no one to keep attracting that debris, whatever that the magnetic materials any further. So things are starting to fall maybe into a truck. So let's say we have a truck somewhere here, right? So it is to be taken by somebody to somewhere else. That's the driver, and right. So let's go that thing. Okay, fine. And it is going to take that thing to some other place. Okay, to make that place a little bit to keep that place a little bit tidy and clean. So that's how it's gonna work. And now at this point, I mean, there's another important application of this using a magnet to take these the unwanted substances away. Now we are using the electromagnet, so therefore only magnetic materials are getting attracted to this, right? Now you can remember something we discussed. We do have metals, but all metals are not magnetic materials. There are metals which are non-magnetic as well, right? So now what if a question will be given in your paper in this way? Now let's say there is let's say there's a place which is full of, let's say, the iron stuff. For example, let's say we do have iron cans and let's say aluminium cans, right? Just for the sake of understanding, 2 examples: aluminium cans and some stuff like that, right? So it's a collection of aluminium stuff and the iron and steel, likewise, right? So now in case you're going to use that the electromagnet, things which are getting attracted, what do you say, are only magnetic materials, right? So now aluminium, even though it is a metal, it is a non-magnetic material. So what do you think? Aluminium cans will not be attracted to that electromagnet. So they are left behind while attracting only the iron cans or steel cans. Did you get that? So don't you feel it is a very nice method of separating magnetic materials from non-magnetic materials? Like the aluminium cans can be easily separated from iron cans or steel cans or steel stuff, right? I mean, by using the magnetism or magnetic materials, or just magnets. What do you say? Yes. So now let me put that thing. So iron cans will be attracted there, right? And then aluminium cans will be left behind. So easily those things can be loaded to another truck and can be taken away to some other place, or probably can be recycled or can be used to make some other products. Okay, right. It's a nice method of separating iron stuff and aluminium stuff. Okay, good. So that thing is left behind. So we can put that in this way. It is just, that thing is left behind, right? Left behind without getting attracted. Left behind without getting attracted. Right. So now you know the reason, why it is not attracted, because aluminium is a metal, fine. One of your friends might say aluminium is a metal, why it is not attracted? Okay, that's fine. Aluminium is a metal, but it is not a magnetic material. It is a non-magnetic material. So all these things, now you are really fine about all these facts. There are metals. All metals are not magnetic. There are some metals, like the few examples just recalling, right? Kind of aluminium, and we do have the copper, and we do have brass and tin, right? These are metals, but they are non-magnetic materials. So these things can be separated very easily from magnetic materials like iron, steel, right? And almost all other metallic materials. So they can be separated very easily by using this method. Okay, that's going to be one of the very important facts which can be assessed or which can be given the priority when it comes to your paper. So just make it a point, right? Because you can answer that very properly. Okay, fine. With that one, we are going to come back to the next one, right? So now, just this slide tries to the kind of like, isolate or just separate the functionality of the electromagnet, how it is going to attract all these magnetic materials, right? Like iron scrap. So how stuff works in magnetic frame, already discussed. Now, basically, just we can write down the functions. Now here we do have the, what's called this electromagnet, right? We can say that's the electromagnet, which is lying inside that housing, right? But actually electromagnet is not magnetized. Why? Because yet it is not powered or supplied with the current. And now this is the circuit which is going to supply the current. So we can say circuit which is switchable, meaning you can switch that thing on, operator can switch that circuit off, right? Okay. So now once switched on, meaning once that current is supplied to the electromagnet, now it is going to become a very strong magnet, so that, it can attract all these the magnetic debris, magnetic stuff like the iron, steel, right? All these cans and scraps, right, into the magnet, so that the operator can take them somewhere else and unload it. That's how things are going to work. Now here, definitely current is supplied. Now that current is flowing through the coil, so that that coil has become a strong electromagnet. Okay. So that explains how that thing is going to work. Okay. Now the steps are again explained here. So electromagnetic, which the large number of coils, it is lying inside the housing, and the current supply, supply is on, it becomes an electromagnet. Supply is off, that magnetism vanishes, then things are going to fall, right? And once electricity is supplied, coil becomes an electromagnet, so that it can attract metal stuff and dump them somewhere else. Simple as that. Okay. Fine. Now, we have discussed so far up to this very moment, okay, when we supply an electric current, so that coil of wire is going to become an electromagnet, right? So, and then after that, how to make electromagnets and how to increase the magnetism or the strength of the electromagnet and so forth, all these things, right? We have discussed it, but one whole thing is left behind. What is that? Magnetism is because of the electricity or the current electricity. Now, actually, we said in case current is off, it is just merely a coil, a piece of, let's say, piece of iron. We can say it that way, right? It's just, a piece of coil, that's all. But when current is supplied only, it gets the magnetism. So by which we can get the idea, a key idea like this. So electric current, right? Or we can say current electricity. Current electricity is the guy who is responsible for what? Magnetism, right? Is the one which is going to generate, we can say, a magnetic field. Is that so? Yeah. So we accepted this fact, and we developed our concepts on that, right? Now what you're going to look into is how people got to know about this fact. Now, what do you mean by about this fact? Is that, when current electricity is supplied, wire can become, or a wire can produce a magnetic field. How people got to know about this thing? That's going to be the subject in upcoming few slides. Okay. So let's see how people got to know about this thing. And developed. Now, thanks to this, the professor in physics, the Hans Christian Ørsted, right, in the 1890. Actually, he was conducting one of these experiments regarding current electricity. Actually, he was too much into that electric circuit. and accidentally there were a few compasses lying in the surroundings, but even the professor did not know about any connection between the electricity and the magnetism, so he did not want to remove all these compasses, so he just left them. Okay, let them to be there because they are not affected. Like that's what he thought, because nobody knows about the connection between the electricity and the magnetism. So that's what that thing happened. But once he switched on the electric current in the circuit, accidentally he noticed the deflection or the movement of the needle of the compass. So he got curious, he got excited, right? And he was it's just he finished his lecture on the subject, and very soon, and then just after that he was on to this one, because that thing was working inside his mind. He again switched on that thing and looked into the compasses. So compasses are going to show the same deflection, right? He switched off, then they came back to their original positions. He switched on, they showed the deflection. My goodness, now we all discussed that compasses are going to show deflections, or they are going to show the direction of the magnetic field, right? So regarding the Earth's magnetic field, we said, okay, that needle, the compass is directed towards the magnetic north pole of the Earth. That's one, right? So that fact was known to all the people. The compass is showing the direction of the magnetic field. But the question was that compass was lying a little away from the current carrying conductor or the wire. So now Ørsted was so excited to get to know, my goodness, there is no connection between that current carrying wire and the compass. But once that wire is supplied with the current electricity, there is a deflection in the compass. So what do you think? What you guess? That current electricity which is flowing through the wire, or we can say, in short, we can say that current carrying wire has produced a magnetic field. So that compass is going to show the direction of that so produced magnetic field. So that's how the foundation was laid, or the invention was done, right, by the Hans Christian Ørsted. The connection between the current electricity and the magnetism. So Ørsted should be given with the credit, who invented the connection between the current electricity and the magnetism. He was the first on the Earth, probably, right? As we know, who laid the foundation, who said for the first time the current carrying wire, right, is going to produce a magnetic field. Okay, with that in mind, let's continue. So this is going to be the tiny sketch of what basically was done by Ørsted. So here we have something called the switch is there, right? So here we have the switch. We can just write that's the switch to switch on and off the current supply. Here we have something called rheostat, right, which is also called a variable power supply, or we can say variable resistor, right? Basically, the purpose of that rheostat is to vary the current. So we can just write the purpose of that one, right? Purpose of the rheostat is to vary, or we can say adjust the current through the circuit. Current through the circuit. That is the basic purpose of the rheostat, which was used here, right? And now we do have the batteries here. So batteries are going to supply the power, and it's going to be low voltage. Usually, why we are using low voltage when it comes to the school laboratories, usually we are using low voltage power supplies, right? Maximum up to about like 12 volts, not more than that for sure. Now, when you have the next visit to your laboratory, just check on the variable power supply. It's usually it's maximum up to about like 12 volts. Now, this is simply because of the fact that if it is not so, then the voltage might be harmful. So therefore, usually in our laboratories, we do have low voltage power supplies, right? Okay. That is something regarding the safety. Okay, and then now we do have actually the Earthstone had the few compasses, as I explained to you in the last while we were going through the last the screen. So a few compasses at different places, and now what's going to happen? Plotting compasses above the wire and plotting compasses below the wire. These compasses are going to deflect, right? Show some deflections depending on the fact that whether the current is supplied or not. Now, when current is supplied, they are going to show the deflection, and when you open the switch, so current supply is cut off, and then the needles are going to get their original positions. So that's how things are going to happen, right? So basically, one important point I just wanted to emphasize that rheostat was used, to serve or to get the advantage to enable or just enabling to vary that voltage. Even though it's a low voltage supply, that low voltage can be varied, right, by using that rheostat. That's the idea. And now, in case somebody will ask, how can we get to know whether current is going to increase or current is going to decrease? Basically, how we can measure the current? That's the question, right? So basically, how we can, or just how to measure the current. How to measure the current? That's the biggest question, right? In this case, so if we have a way to measure the current, so we can see, okay, the indicator is going to go, or indicator is going towards the bigger numbers. So we can say our current is increasing. It is going down. So we can say current is decreasing. So we can for sure we can say current is increasing, current is decreasing, and likewise. So how we can get this thing done, right? So the answer is, we have instruments which are dedicated for the purpose of measuring electric currents. So these gadgets, equipment, right, are known as ammeters. Okay, so if I'm going to write that thing, so we call them ammeters. Right. So now the circuit symbol of the ammeter is going to be we're going to draw a circle, right? If you happen to draw that thing, fine. Okay, so we're going to draw a circle, and then we are going to write capital A in the mid, and we can have two terminals, right? It is getting connected to on the right side to that terminal, on the left side to this terminal. That's going to be the circuit symbol of the ammeter, right? So I'll just write that part as well. For the sake of your understanding, that's going to be the circuit symbol of the ammeter. So we do have the circuit symbol of the ammeter. That's how we are going to symbolically represent ammeter in a circuit, right? That's because we can't draw now. So you can see here we do have the practical, the gadget, right? So that's the look. That's how an ammeter looks, right? So it is too difficult for you to draw that entire the gadget in a circuit. So it takes time, and probably we are getting distracted while drawing that thing, right? So instead of that, we are using these circuit symbols to convey the idea. Now here we have an ammeter to measure the current. Now the whole entire purpose of this ammeter placed here is to measure the current flowing through it. Okay, so now in case there will be a question in your paper, ammeters are used for, or else how to measure the electric current flowing through a wire. So what is the direct and confident answer by you? By using an ammeter. So the purpose of the ammeter is to measure the current through a component, right? Okay, that's it. Now this is that's the experiment which was conducted by the Ørsted, and basically he observed when current is flowing, there are deflections. When current is not flowing, they are going to be, compasses are going to get into their original positions. So therefore there should be a connection between current, electricity and magnetism. Okay, so therefore that foundation was, the very foundation was laid by the Ørsted, right? The connection between the current, electricity and the magnetism. Okay, that's about that thing. And then with that we can get into the next important thing, right? So that's going to be, now we know by now we know the fact when there is a current flowing through a wire, that wire is going to produce a magnetic field, right? Now at the same time we know the fact that okay, we can't see magnetic fields, they are invisible, right? But yet we can illustrate or we can show how this magnetic field is by using, lines, right? And we talked about these properties of these lines as well. They are imaginary lines. They are starting from the north poles and they are towards the south poles, and they are accompanied by the arrowheads. These arrowheads are showing the direction of the magnetic field. They never touch, they never cross, blah blah blah, right? Where they are closely packed, there we have the stronger magnetic field. Where they are loosely packed, there we have the relatively weaker magnetic field strength. Likewise. So those were the important properties associated with the magnetic field lines. Now, here we have a wire which is carrying an electric current, and so now we know there should be a magnetic field. Now that magnetic field is invisible. So in case we wanted to identify how that magnetic field is going to be, the shape of the magnetic field, what we can do. Either, now there are two ways we discussed, right? So number one, just say the method number one, as we have already discussed, you can use, you can sprinkle or spray iron fillings. What do you say? Yep, iron fillings can be sprayed in the surroundings, right? Or as number two, little more scientific method, you can use floating compasses, right? Bunch of floating compasses can be used, right? And by using the direction, shown by the needles of the compasses, so we can keep drawing lines, so thereby visualizing or just figuring out the shape of the magnetic field. Now here is a current carrying wire, right? So it's a straight wire here, so that current is flowing upwards. Now magnetic field pattern, the shape of the magnetic field, right, is going to be circular. So now these blue circular lines, right, are the magnetic field lines, as the shown here. They are the magnetic field lines, right? And these arrowheads are standing for the direction of the magnetic field. Isn't that so? Something we have already discussed, right? So that is going to be, okay, the arrowhead shows the direction of the magnetic field, right? Shows the direction of the magnetic field. Well, that's also something we have already discussed, right? So just what I want you to know in this case is that the current carrying wire is going to have a magnetic field, right, whose shape is going to be circular, which can be represented by a set of circular line segments. So just something like the circles, right? Okay. Now capital A is here, capital B is there. That is because of the fact that now somebody is going to look into this magnetic field pattern, let's say from the top, meaning from the letter capital A, and meanwhile somebody else is going to look into the magnetic field pattern, or is observing the shape of the magnetic field pattern, from B. Now the observer who is going to look from A, let's say observer A, and the one who is observing the field pattern from B, let's say observer B or B, right? Now let's see how these two patterns are going to be. How the observer OA is going to observe, or what observer OA is going to see, and what observer OB is going to see, right? So we can, look into these the field patterns. Okay, fine. Here we go. Magnetic field pattern around the wire, according to the observer OA, as we have declared in the last slide. So this is how he is going to see the magnetic field, and this is the observer OB. This is how he is going to see the magnetic field. Now this dot represents that electric current is coming out of the board. That cross represents electric current is going into the board or the plane, right? Now it is mentioned here, current out of the plane of the paper, and here current into the plane of the paper. Now these dot and cross, these things are conventionally used, right? The symbols which are accepted worldwide, internationally recognized symbols, right? We are frequently used in physics. So Udala, you will learn about all these the symbols and additional symbols, right, which are used the worldwide and which are internationally recognized in your due course. Just for the time being, I don't want you to pay attention to these symbols, right? Just what I want you to get to know, understand is this. Now the shape of the magnetic field pattern is going to be circular. So circular, what do you say? Yeah, lines, or just we can say circles have to be drawn, right? So we keep drawing few circles like that, right? And you have to observe, you have to stick to one of the very important properties while keep drawing away from that current carrying wire. Now wire is going to be somewhere there here, right? You get that? Wire is going to be somewhere there here. Let's just give it a color. That wire is going to be somewhere there. So, well, let's say that wire is represented by this the green color circle. Now while you keep drawing these circles, right, and while going away from the current carrying conductor or the wire, can you see something really obvious, if I ask that way? Now, for example, here, the gap between these two line segments and gap between these two line segments and gap between these two line segments, right? Meaning the separation between two consecutive lines increases while going away from the wire. Here we do have the wire with that green color. So you keep going away from the wire. So you have to make sure you keep drawing the circles, right, in a way that separation between circles increases while going away, right? So that now if you take a certain area, let's say for example the certain area somewhere there here, okay, that much, and if you take the same area somewhere there here, now the field lines are tightly packed here than there. So what do you understand? Something we have already discussed. Field lines are closer to each other where magnetic field strength is greater, right? So therefore here it should be, the stronger magnetic field than there. Same thing is held true regarding the other figure as well. Now actually these two are the same diagram, right? Same magnetic field from two different points of view. Okay, so now let me just write one important thing here. So let's say here we have the stronger magnetic field. Stronger magnetic field. Magnetic field is stronger there, right? And here we have the magnetic field is less stronger. Magnetic field is less stronger. Okay, right, fine. So that is regarding this area. So same thing is held true regarding this the other figure as well, right? So just here, if you get let's say line from the mid there, and line from the mid, and line from the mid, like that, right? And I'm going to take okay, what if? So that gap and this gap, right? And the gap here. So you can see they keep increasing, right? They keep increasing. So while going away from the conductor, the separation between two consecutive or two adjacent field lines should increase to represent the fact that while going away from the current carrying wire, the strength of the magnetic field decreases, right? That's the conclusion. So let me write the thing, here, something really important, right? So we can say, so while going away from the current carrying conductor or current carrying wire, the strength of the magnetic field decreases strength of the magnetic field decreases, right? So that's what that's the most important fact I want you to understand. So that's while going away, this question, while going away, so strength decreases. Going away from the current carrying wire, then strength decreases, right? Okay, so how we are going to present that thing, by using the field pattern or the field line diagram. Okay, we have to draw the lines in a way that, the spacing between them increases while going away from the current carrying wire. Okay, and that's about that. And then we can just recap what we have discussed. Mainly what we have discussed there, right? So we can say the summary, right? Basically, so we talked about the magnets, and then we do have permanent magnets, we do have the electromagnets, and permanent magnets are usually made by iron, cobalt, nickel, steel, and alloys, special alloys like the alchemax, alnico, ticker now, and I told you, don't forget, you have to remember this one because probably they are waiting to check this, right? Neodymium, right? So something called neodymium, one of the strongest magnetic the materials, and it is also an alloy, right? Frequently used to make permanent magnets. And now permanent magnets, they remain as magnet, or just magnetism prevails even after it has been used. Okay, that's why they are called permanent magnets. Okay, now electromagnets made by a wire coil, right? Okay, and then they should be supplied with an electric current, then and then only it gains its the magnetism, or it becomes into a magnet. And probably that is the that is also the advantage of the electromagnets, over the permanent magnets. So we can switch on and switch off the current supply. So thereby we can switch on and switch off the magnetism also as we want. Magnetism remains only until current passes through the coil, and therefore magnet can be switched on and off. Ultimately, we are coming to the point, right? So this is going to be the major advantage of the electromagnets over the permanent magnets. Okay, fine. Now with that one, so we have seen, some of these, right? The uses of the magnets, now loudspeakers, then the cassette tapes. Probably nowadays we are not using them because we do have these flash drives and hard disks and all, right? So then again, hard disks are there, headphones are there, and magnetic letters, probably the stuff we played with, right? And sometimes we use them to learn ourselves numbers and letters and adding numbers, subtracting numbers, all these stuff, right? And in addition to that one, the MRI scanners. Now MRI stands for magnetic resonance imaging. So probably the maybe you have somebody who has undergone one of these or who has been subjected to MRI scanners, these scans. Now MRI scans are done in order to reveal very the say the important and very accurate information the inside the body, especially when it comes to the brain and the other organs as well, right? So MRI scanners can produce especially one of the important things you should know, the 3D images. Now 3D means three-dimensional images. Right now, for example, let's say X-rays. Now probably you have heard about X-rays and ultrasound imaging. They are going to be two-dimensional scans, right? So now three-dimensional means like we can see more information. We can just gain more information about the figure, right? Okay, so MRI scanners. So it is about 3D scans, three-dimensional scans, 3D scans. Right, okay. So now that capital M stands for magnetic resonance imaging. Magnetic part is there, right? Resonance imaging. Compasses something, we have the, we were talking about these guys and we were using them, right? So throughout the entire session. So ultimately we got to know, my goodness, the connection between the current electricity and the magnetism also was established by the Hans Christian Ørsted, simply by using accidentally observed deflections of a sequence of the compasses, right? Okay. And water pumps. Now again, when we say water pumps, actually they are motors. Now pumping is what we observe, right? Probably from the well to the overhead tank, water is being pumped. That's what we see, that's what we observe. But actually what is working inside is a motor, right? So therefore pump is, essentially is a motor. Now again, motors are the, we have discussed it, right? At the heart of the motors, right? We do have the magnets there, especially when it comes to industrial magnets, industrial motors, like the high capacity motors, we use electromagnets. Like dynamos, right? Dynamo is a generator, but bicycle dynamo, right? So probably you have heard about that thing, bicycle dynamos, and we're going to talk about details of these things in due course, right? But just for the time being, the bicycle dynamos, they have sometimes permanent magnets, right? As well as electromagnets as well, right? Okay. So it's about the now when we talk about the water pumps, it's all about the motors, right? Okay. So now with that, okay, we can look into some of the sophisticated examples. Now, actually, I wanted to just put that thing into a different screen simply because of the fact that we can hold these examples, right? Kind of like modern, or probably we can say sophisticated. Right, meaning most of these things are used so frequently nowadays, right? Not like previous days. Now, for example, these magnetic stripers, you have seen these debit cards and credit cards, right, being used by your parents. I mean, probably in these supermarkets, right, to pay the bills. So what they are doing, just they stripe that thing, or just probably they hold that thing closer to the machine, so that machine is going to send some radiation which can be detected by the magnetic field of the the card, right? Or that reflection is going to reveal the data the encapsulated inside the card, right? So magnetic stripers, they are using, obviously by its name, it's self-explanatory, the magnetism is used there. And magnetic cranes, something we have already discussed. Magnetic doors, one of sometimes we are playing with these things as well. Here we have the magnet, and some kind of magnetic material, like a piece of iron, is attached to the door somewhere there. So when they are getting closer, so that magnetic material is getting attracted while closing the door. And here we have probably the most sophisticated application, right? Nowadays, we don't have, unluckily or luckily, we don't have them in Sri Lanka, right, for the time being. In our country, probably we can accept them within another maybe 1,000 years. So now, maglev trains. Now, maglev stands for magnetic levitation, something called magnetic levitation, or magnetic levitating. Now, magnetic levitation is just to be used mag part there and lev part here, so hence the name maglev trains. Now, in magnetic levitations or maglev trains, they use a special technique. Now, usually in our trains, you have seen so many times, right? Our trains, they are running on railways, right? Rail tracks, and wheels which are made out of steel, sometimes some different materials, right? But anyway, metals, they keep rolling, rotating, right, in contact with these metallic rails. So we have a huge sound, right? At the same time, something probably you have heard, friction, opposition for the motion is there. And so too much of power is lost because of these the frictional forces, right? So that thing is highly avoided by these maglev trains simply by doing something like this. Now they make rail, let's say rail track is there, and it is also going to be a magnet, right? I'll make it that way. And then let's say if it is a magnet, it should have poles. So let's say, for example, here we do have the North Pole, and here we do have the South Pole, right? And then after that, they have the what's called this train. Somewhere there here, that's the passenger compartment, right? People are here. So we can say, okay, you are there, and I am here, and so on, so forth. And then after that, it is connected to another magnet here, different color, And somewhere there here we do have another magnet which is connected to the body of the maglev train. Right. Now, what's going to happen in this case? Probably, as you can guess, right? These are electromagnets, right? All these are electromagnets, and they can make, okay, they're going to supply the electricity in such a way that that electromagnet is going to have a north pole at its, bottom, somewhere there here. And therefore, as a consequence, come on, south pole will be somewhere there here. Now, can you remember we talked about the magnetic rules, right? So let's say like that makes the things pretty clear. Now, what's going to happen? Now, we talked about the magnet rules. So we say like poles repel, unlike poles attract. So now what's going to happen here? Here we do have the North Pole again, come on, close by another North Pole, so they try to repel, right? So we're going to make that supply current or the current supply is made as big as possible, right? In such a way that these repulsive forces will be able to lift or hoist that passenger compartment a bit above. Not by kilometers, not by meters, but by probably, come on, a fraction of a millimeter. That is more than enough, right? So that thing will be lifted up. Say this thing will be lifted, okay, a bit by leaving a gap between the what's called this railroad or the rail track and the passenger compartment. There are locking mechanisms, separate locking mechanisms. So therefore, passenger compartment is not allowed to, go the sideways, right? So that security is there. Now, when the engines are going to engines are going to function, or just something like when the train is powered, what's going to happen? It seems now this is a passenger compartment which is hovering in the space, right? So no metallic contacts are there. So what do you think? Just it can be something. Just think about a balloon which is suspended in air. By a small force, it can be moved. So therefore, now once the engines are powered, so the passenger compartment, that means the maglev train, is going to move magnets with so high speeds. Like very, very high speeds. So usually these are moving with speeds in the range of like let's say the 200 meters per second, right? Just within 1 second, 200 meters will be covered. It's just like, so it is just, it's very difficult for you to, identify, recognize even the letters, right, written on the body of the train and the windows and what compartment is moving right now. It's very difficult to identify, recognize why, because it's moving that fast, right? So 200 meters per second, sometimes somewhere around 280 meters per second like speeds. Very, very high speeds, right? So we don't have that experience right now. At the moment in our country. Okay, fine. Probably let's have the hope to have them very soon in our country. Okay, now just one more thing for you to compare this speed, right? Now you have probably gone through you have gone through about sound waves in the waves section, about which I'm going to do another presentation like this, right? So that it will be helpful to you. So the speed of sound waves in air is usually in the range of the 340 meters per second, somewhere around 330 to 340 meters per second. It can vary depending on some other external factors like humidity and the gas and like wind, right? Temperature and like facts. Those are not relevant right now. But I just wanted to point out these values: 330 the 340 like values, right? For you to compare the speed of the maglev trends. See, 280 is little closer to 330. So maglevs are moving almost at the same speed as that of the sound. So they are moving so fast, right? Okay. So therefore, I mean, these kind of high speeds were possible to achieve, right? I mean, just because of the, I mean, magnets. Actually, come on, the usage of the magnets. So one of the very sophisticated the developed applications, right, in which we are using the magnets at the heart of its function is maglev trends, which is going to make our transport so fun as well as so quick at the same time. Okay, so that's all about the uses of the magnets, and with that, I think we have come to the end of the presentation, right? We talked about the magnets and almost all about magnets, and come on, ultimately we discussed the almost all about the applications in which we are using the magnets, right? Okay, I think we got the massive knowledge, thorough understanding about this concept magnetism, which comes under the unit number 13 in grade 8. And so just before winding up, and until I'm going to meet you very soon with another presentation like this, right? I really want you to go through the material one more time, right? And to refer to your books, right? And making yourself too much ready, right? In advance, very important. Make yourself ready in advance, right? For upcoming examinations, to make sure to secure very high marks possible, right? It is not becoming the second of the class or to place yourself at the, I mean, like to get the first of the class. That's not the thing. Instead, achieving maximum possible amount of marks for each and every subject, right? Okay. So now so having that the intention in mind, so wish you all the best, and I think you'll be able to, I mean, get the maximum out of this presentation. You will learn more about these fantastic concepts in detail in upcoming courses. In case I'll be able to, I mean, meet you in upcoming courses. So I'm going to teach you the magnetism, come on, yeah, with much more details and really much more fantastic and practical concepts, right? Okay, so wish you all the best, and dedicate and sacrifice and commit for your results to score maximum marks, and have a nice journey. So till we are going to meet with the next presentation, I'm going to say you bye and wish you all the best. I am Nalin Koralagi, and I'll meet you next time with a new presentation. Okay, thanks for watching.